I will be deriving the Michaelis-Menten enzyme kinetics in this video. In this mechanism, S is the substrate or reactant, E is the enzyme, ES is the enzyme substrate complex, P is the product. ES is involved in 3 elementary reactions, and if we can assume this ES is highly unstable, we'll be able to apply this steady state approximation. To ES, which is simply the change of ES with respect to time, is roughly 0. And also, ES is involved in 3 elementary reactions. It's produced in this forward reaction, so we have the first positive term. And ES is consumed in this backward reaction, so it's going to be minus. And also, ES is consumed in this K2 reaction, so minus K2. Yes. I'm assuming this is the first order, and this backward direction is also the first order of ES, and the first, this K1 reaction is second order. So if this is 0, we can easily get an equation for ES in terms of the concentration of the substrate and the concentration of the enzyme. So basically, ES is equal to K1 over K minus 1 plus K2. And then times S times D. So this part is complicated, but if we set a composite constant, uppercase K, if we set this to be K minus 1 plus K2, the bottom here over K1, okay, so if we use this, we can simplify this equation to K sub M times ES equals E times S. Again, this E and S are the concentration of the enzyme and the substrate at time t. If we are talking about the very early stage of the reaction, we can make some approximation here. So first, we're going to look at this concentration of E. So if we look at the concentration of E, it's actually the initial concentration of E, which is E naught. This means times 0 minus ES, because if you look at this, the enzyme can exist in the form of this enzyme itself or the complex. So the initial concentration of enzyme minus the concentration of ES will give you, well, the actual concentration of the enzyme at time t. And then if we look at the concentration of the substrate at time t, it's the initial concentration of the substrate minus ES, right? Because again, once the reaction starts, this S can be in the form of just itself or in the complex or converted to P. So we'll have to do this minus P as well. However, if it's at very early stage, so T is very close to 0, and then P is very close to 0. So at the very early stage of the reaction, the concentration of the product is 0. So we can just get rid of this term. And then we combine this ES term. Where's the, over here, we can simply just get the concentration, initial concentration of E, initial concentration of substrate, so this times this, and then minus ES, the concentration of ES, times this guy, and the concentration of ES times this guy, so basically it's just E naught plus S naught here. There's another term, which is negative ES times negative ES. So. All right, and again, we mentioned that this ES is assumed to be very unstable, and that's why we apply this steady state approximation to ES. So if it's very unstable, the concentration of ES is very small. So this term is much, much smaller than this term. and this term is much smaller than this term as well. So anyway, we'll just neglect this very small ES squared term. So now if we look at this, we have the concentration of ES here, the concentration of ES here, and we're going to combine everything, and we have the expression for ES. We'll put it here. The concentration of ES again is equal to E naught on top, S naught on top, so this guy on top. On the bottom we have this composite equilibrium constant. The definition is here. M stands for Michaelis-Menten, and plus E naught plus S naught. All right, typically we can assume the initial concentration of the enzyme is much smaller than the initial concentration of the substrate. And then we have, well, this is approximate as well. And then we have this equation for ES at, again, the very early stage of the reaction. All right. So now we're going to look at the reaction rate. The reaction rate is how fast we can produce P. So reaction rate is K2 times ES. And we're going to plug in this expression for ES. It's going to be just K2, E naught, S naught, divided by Km. M stands for Michaelis-Menten plus S naught. All right, so if you look at this reaction rate, it is proportional to the initial concentration of the enzyme, but it is not linear to the initial concentration of the substrate. And we can simply plug in this S sub 0 to, if we assume the initial concentration of S0 is 0 and then R is 0, the reaction rate is 0 if there's no substrate. But what if the initial concentration of substrate is infinity? Well, that gives us a infinity reaction rate. Actually, the answer is no. If this initial concentration of the substrate approaches infinity, this guy is much bigger than Km, so we can neglect this Km. And then S naught cancel each other. So the maximum reaction rate when S naught equals infinity is equal to K2 E naught. It's not infinity, it's K2 times E naught. It's proportional to the initial concentration of the enzyme if we have an infinite amount of the substrate in the system. And again, if we look at this, it's pretty hard to do data analysis. If you have experimental data of R and experimental data of S naught. Again, because this is because S naught appears on top and bottom simultaneously. So how can we make it a little simpler? I'm going to erase this steady state approximation and some part of the derivation, and then I'm going to take the first the reciprocal of both sides. So 1 over R, the reciprocal of the reaction rate, is equal to Km, the composite constant, divided by K2 E naught, S naught. And then this guy divided by S naught, E naught, S naught. And obviously this to cancel. And we know that the maximum reaction rate is equal to K2 times initial concentration of enzyme if we have infinite amount of substrate. And then we can easily simplify this equation to be 1 over R max. So this guy is R max. And again, 1 over this is R max. And this is a very useful equation if you plot 1 over R versus 1 over S naught. So you'll see that this part 1 over R max is the intercept of the plot. Km over R max is the slope. So this is the intercept, and the slope is positive. It's the composite Michaelis-Menten equilibrium constant over Rho max. Done.